All right, so
she's like, we're on a schedule. Let's take me out of here. I don't want it. Yeah. I don't know. So many gigs
on. So grades for the second part of the test will hopefully be available tomorrow. We'll see how it goes. I want to get all of them done before I tell next week. So plus we have a couple people that either weren't there yesterday or weren't there Tuesday, or both, that need to get caught up and get some things done. So but today's my grad school day. All my stuff is due today on Thursday. So that's my focus tonight when I get home from we have a baseball game and a raffle. So we'll see if I can get them done tonight. Certainly this weekend, and then I'll as soon as I get them done, I'll put the grades in for you. How did you think it went yesterday? Yeah.
I'm not gonna lie to you. I walked out of class crying.
Pretty bad, huh? Yeah. It's one of those things you get it or you don't in the moment. You remember what to do or you don't, and if you're kind of stuck, that can be kind of tough. So that's why I want to start chapter 3 right away, get to a point where we can get another grade in there as soon as we can. So you'll see. Take out these guided notes if you haven't done that yet. Does anybody need the guided notes because they didn't get that to me yesterday? Okay. Put your name at the top so it doesn't disappear on you, because this is at least the next couple weeks for sure. Wish week next week, and then testing week the week after. You guys see that CMAS was canceled? Yeah. So the juniors it only affects you. So the science state mandated test for juniors, the CMAS, is not happening Monday the 12th. So that's gonna be just a regular school day. Okay, so our testing week is really only Tuesday, Wednesday, Thursday. PSAT 9, PSAT 10, and then SAT for juniors. I don't know the order. I don't know what comes first, but I think it's SAT Tuesday. I think that's right. And then PSAT 10, and then PSAT 9. I think it was 11, 10, 9. Yeah.
Are we having half days or what?
It's not even half days. Our classes in the afternoon are like total an hour. So we'll have 1, 2, 3, 4, 5, 6, 7, 8 homeroom, something some combination of those nine periods in the afternoons for 20 something minutes. Yeah. So Tuesday, Wednesday, Thursday will basically just be take your test, and then everybody's remote all week long unless you're taking that test on that day. Then you'll come in. So you will only be in school on Monday, and then at most one other day. Seniors, you just come in on Monday, and that's it. Juniors, you just come in Monday and I think Tuesday. Sophomores, Monday and Wednesday, I think. So we'll talk about that more next week as we go. But let's get to it. What you'll see in chapter 3, unit 3, whatever, is it's kind of broken up into 2 sections. Okay. These first 3 lessons will probably take us, let's see, Thursday, Friday, Monday, Tuesday, Wednesday, at least I would say the next week total, Thursday to Wednesday. Time to practice and working on stuff like that. I don't know if we'll do an in-between quiz. I might offer one for those of us that want another grade in that test category, so that it dilutes that assessment category a little bit, so that if you did not do well on test 1 or test 2 or something like that, you get another grade in there as soon as you can. And then second half right here, I'll work on some other stuff, exponentials and logs and other transcendental kind of stuff. I'll probably skip a little bit. I'll probably skip derivatives of inverses completely, just for the sake of time, so that we can get onto chapter 4 when we can do applications. Okay. And what you'll see, unit 2 was understanding the derivative, just getting a first understanding of, okay, this limit of this slope, right? Limit of the difference quotient. And we just let that limit go down to 0, that distance between those 2 points. And we figured out this really, really nice shortcut if we can write it as a polynomial. Right? If I can write something as a polynomial, then I can use the power rule. And what you'll see in chapter 3 go ahead and turn the page if you're still on the front page. Go ahead and turn to page 182. What you'll see in this chapter is we try to figure out some other rules for, and there's that word I said a couple of days ago, differentiation, to find the derivative. And there's three big ones. Okay, three big ones that we're going to deal with here in the first half. Today and probably tomorrow, we'll just focus on one. Okay? Especially with tomorrow being Friday already, right? My goodness. Being a short day with late start Friday. Again, late start Friday there. So first period's not till 9 o'clock. We'll probably do what we can today to learn it. We'll take tomorrow to practice it. And then we'll move on next week. So let's take a look. Finding the derivative of a product of two different functions. Right, so f of x, yeah, they call it a one function, but like there's this function here, this linear one, and this quadratic right here. So cubic total, right? Linear, quadratic. How could we do that? Like, can we take the derivative of that right now? What do we need to do?
Multiply and then do the power rule.
Yeah, perfect. Let's unfactor. Let's distribute. Like, let's get it out of this factored form. Let's expand things out by multiplying it out. So let's deal with just the function, right? So f of x equals. Let's multiply this out and see what we get. So everything from the first goes to everything from the second. All right, so you got a binomial times a trinomial, so that's 2 times 2. So 6 total terms here that we're going to have. So go ahead, try it out, see what you get. Let's just multiply these out. I always do like the first term and the first one through all of them. So I'm going to do the 2x through everything. Make sure your coefficients and your exponents adjust as they need to. Then I do the -3. And knowing that I had a binomial times a trinomial, 2 times 3, I'm going to end up with 6 terms there. 1, 2, 3, 4, 5, 6. I know I didn't miss it. Nice. All right, at least no parentheses left. That's good. Should we take the derivative now? What should we do? Yeah, like terms. Yeah, let's put anything together that goes together. You know what you're talking about. It's words. Mouth words, I know. Yeah, mouth words. Let's put together anything that goes together. If we're gonna put them together, what order do you think we should put them together in? We had to make a choice. Biggest exponent on down from there. So biggest exponent here is cubic. The degree 3 term right there. There's no other one, so just 2x cubed. All right. Quadratic next. So anything quadratic. Okay, -7x squared and -3x squared. So put those together, negative. So 4 and 3, -7. And then my x's, okay, 2 and 6 is 8. And then my constant at the end, -3. Cool, there's a function. That's a nice one. And look what they asked us to do, right? Rewrite the function f of x as a cubic. Then find f prime of x. Okay, I can do that. Now we're feeling pretty good. Now I got a really good look for this. Go ahead, give it a shot. Make sure the power rule is still fresh in your minds. Let's see what we get. I'm going to write it down over here. When I scroll down, I'm going to lose it. F prime of x, 6x squared minus 14x plus 8. Thank you for not making me do that with limits. I appreciate that. Now, everything I'm going to show you comes from limits, but my goal for the rest of the year is to never write a limit again. That's my hope, is that I never have to write a limit ever again. I just want to come up with some nice rules that we can do that. So what does that represent again? What is that? What is f prime of x? Going back to like a chapter 2 mentality. What is that? Slope of the tangent line anywhere on that cube. Okay, all I gotta do is plug an x and I can find the slope of the tangent line. So nice. And another thing, another way to say that, and I think this is going to be even better, it's the rate of change of the function at that point. If I was following a point that was moving along that function, if it was a particle all rolling down a hill, you walk up and down a mountain, how fast are you changing? How fast are you going up? How fast are you going down? Cool. And is that hard? Was that difficult? No. And so I like that way, right? If you give me a function and it's represented as just a product of a couple things, and they're both just easy polynomials, I'll probably just do it this way. I'll just multiply it out, simplify, and then take it out. Now, our boys, we got our two boys right back in the day, late 17th century, Isaac Newton, Gottfried Leibniz, there they are, fine. I think for the first time we actually have their names written down. These are the two that developed the study of calculus kind of separately. And then latter half of the 17th century, Leibniz was actually the first to give us what's called the product rule. That says, hey, if you don't want to do all of that work to multiply stuff out first, or you can't multiply it out for whatever reason, we can get to the derivative right away. Okay, whether you decide that it's easier or harder, that's up to you. But we have a way to do it. And so I'm gonna fill up this box here, this product rule, with two different versions. And it's the latter version that I think I'm gonna use more. But I want to give it to you both ways for those of us that like function notation versus not. Okay, and I could prove this with limits. I'm not going to. You can thank me later. If we are given a function like some y equals, and it is the product of two functions. Now I could have called that like if h of x equals f of x times g of x, or if f of x equals g of x times h of x, right? A function defined as the product of two different ones. Okay. Then the derivative of this, so I'm going to call it dy dx rather than y prime for a lot of reasons. Number one, this is the most popular and most common notation for derivatives. Also, it's an homage to our boy Leibniz, because that's his notation, and this is his product rule. So I'm going to give you a check. Okay. But since I call it f of x and g of x, I'll just stick with like f prime, g prime as I talk about this. And man, it would be so nice if it was just f prime of x times g prime of x. That would be amazing. It's not. There's more to it. Okay. It would be really nice if, you give me a product, the derivative of that is just multiplying them together. It doesn't quite work. The limit doesn't play into our favor. But yeah, it's not super crazy, which is so here we go. What you're going to see is f prime and g prime are going to be in here, but f of x and g of x, the two original pieces, will also be there. Okay, so you're gonna see an f of x, a g of x, an f prime of x, and a g prime of x in a certain order. Okay, and what you'll notice is that the only connections that I'm going to make are with multiplication and addition, and the order doesn't matter for any of them. Okay, so I'm going to give you my order. Okay, but if you looked up the product rule online with function notation, they might flip-flop with addition, they might flip-flop with multiplication. It's all the same. But I'm going to give you an order that I like, because when I give you the second version, I'm going to stick with that order, and that's the one I'm going to use over and over. Okay, here we go. dy dx. Okay, the derivative of y with respect to x, look, our variables are x. This is f of x times g of theta. We'd be in real trouble. Okay, we are not going to mess yet with multiple kinds of variables within one function. We're all just going to stick with just x, or just theta, or just t, or whatever it is. Here we go. Okay, regular f of x, just plain old f of x, times, so here's where the order doesn't matter, because it's just multiplication, but this is the order we're going to go with, times g prime. That's our first term. Okay, f of x times g prime of x. It's also way easier to memorize my latter version. I think you like that better. Plus, again, there's addition's commutative. Who cares what order I put this in? This is the order I'm going with. So two things being multiplied here. I'm going to do two things being multiplied here as well. Okay, original g of x times, what's the only thing I'm missing? There it is. And that is the product. Okay. I'm going to give you one that we're going to use way more often. Okay. But they're one and the same. It's just, do I use function notation or do I not? Okay. The thing about this, like, okay, I'm using function, like this is Newton's notation here, this is Leibniz's notation. There's no way I'm going to mix those together if given the choice. And so I'm going to write a slightly simpler and identical version to this, okay, where I'm just going to define this y equals in a much simpler way without any function notation, okay? Two things being multiplied together. I'm just going to give those two things simpler names than f of x and g. And I'm going to use some letters that we really don't use very often as my placeholders, my variables. I'm just going to do this substitution. So I'm not writing functions. And you know, x and y, even z, pretty common. T for time, a, b's, and c's for constants. I want it to be towards the end of the alphabet because that's for variables and unknown things that could be changing. And so the two letters that I'm going to choose, and this is not me choosing it, but kind of the world of mathematics, u times v. I'm just going to say, okay, whatever the first factor in that product is, I'm just going to call it u. And it's just going to be some function, whatever it is. And then same thing for v, the second part. Okay, so u and v. Toward the end of the alphabet, which is nice, but it's not x and y, which is okay. So if that's my original equation, then, okay, now I can write dy dx. That's nice. And let's see if we can match things up. Let's see if we can create this version. So basically what we're doing is we're saying, okay, f of x is u and g of x is v. That's basically what we're saying. Okay, so look at the version in blue for the derivative and see if we can kind of alter it to match our u and v setup. What's the first thing after that equal sign? U, right? F of x, okay. Just whatever the first thing is, right? U. Times v prime, right? Well, but we're not going to write v prime. I want to stick with kind of the dy dx kind of setup. So don't write v prime just yet, but that's exactly what it is, the derivative of v. Now, if we're doing dy dx, right, the derivative of y with respect to x, when I individually just kind of take the derivative of that second factor, whatever it is, what is the variable that I'm going to take the derivative with respect to if it's dy dx? Like, am I going to take the derivative with respect to theta here or with respect to t? What am I taking the derivative with respect to? It's got to be x. If I'm defining this to be dy dx, my entire derivative is all with respect to it, if I can, right? And so what I could write right here, right now, is I could say dv dx, the derivative of v with respect to x. But we're mathematicians. We're even lazier than that. Of course, I'm taking the derivative with respect to x because I've defined it right here. So instead of going through the trouble of writing dv dx, I'm just going to write dv. But it is with respect to x up here. And when I do my derivative, I'm actually going to, I'm going to write it down. But I'm just going to label it dv, knowing that you know that my variable of differentiation, you say it fancy now, is going to be x. Okay, so u dv, u times dv. Okay, so there's u, there's dv. What comes next? Plus, okay. Now, just plain old g of x. What did we call that over here? V, okay, times. So what do you think we're going to say for f prime of x here with our u's and v's? Du. Now, yeah, it's du dx, but I'm just going to write du. That is the one you're going to hear me say all the time. U dv plus v du. 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 That is what you want to get stuck in your head. U dv plus v du. That's the problem. I can show it to you with limits. That's exactly what it would turn into, which is amazing. And now we can use it, okay? That if we've got this function and it's written as a product, I'm going to scroll up so I got more space if you don't mind. okay? If we've got this function that is written as a product, right, 2x minus 3, and x squared minus 2x plus 1, if we can either, like make the choice that we want to use the product rule, or maybe we're just stuck and say, I can't multiply stuff out like we did in the original one to get to that original f prime. Maybe we just say, okay, I'm going to decide what I want u and v to be. I'm going to make this choice. I've got two things being multiplied together, and I'm going to say, you know what? I'm going to let u be 2x minus 2. And what I'm doing over here on the left is something I do all the time with these rules that you're going to see over the next week. I kind of come off onto the side, and I'm going to say, okay, I'm going to label what I want u to be. I'm going to label what I want v to be, x squared minus 2x plus 1. I'm going to make that choice now, because what I can do then right underneath u and v, so that I'm not doing it in the middle of the problem, but I'm kind of taking a second to do some side work, I can figure out what the derivatives of those are separately, and then jump into the product rule and just get out. And so this setup over here, with u equals v equals du and dv, I do it every time. Every time I use the product rule, and the other two that you'll see, I'm going to do it all the time. Okay. Eventually, you might get to the point where you can do it in your head. Great, do it. Okay. But writing it down is never a bad decision. All right. So what do you think? What is du, which is du dx, the derivative of u with respect to x? Okay. And what about dv? 2x minus. And now that I've got the four pieces of the product rule, now I can just jump in. I'm going to erase this e times v so I can give myself a little bit of space. And what I'm going to do, just so we see it again, okay, f prime of x, only because they called it f of x, so fine, I'll just do it. I'll call it f prime of x. But right there, dy dx is a great choice. If you want to just stick with dy dx, that's a great idea. And those are interchangeable. I actually had that question come up as people were kind of getting prepared for Tuesday, Wednesday. A couple people said, when can I use which one? Like, are they just the same? Can I mix them and match them? Absolutely. That's the short answer of that is they are one and the same. It's just that dy dx is a lot more common for what we're going to do. So call it f prime of x. You'll see I'll start mixing some dy dx's as often as I can. You just have to watch it, because what if it's theta, then it's dy d theta or dy dt? I'm going to make sure our variables are right. I'm just going to write this one more time. U dv, put the dot in between if you like it. You don't have to. Plus v du. But there's the product. And all I need to do is make it happen. Four pieces. So I'm going to have four sets of parentheses kind of lined up next to each other with the plus in between. So here comes u, 2x minus 3. Here comes dv, 2x minus 2. Right? There's u dv. Whatever I decided u was going to be, whatever I decided dv was going to be. Now, if you look this up, you might find that if you Google the product rule, there might be a website that says vdu plus udv. Same thing. Either one. Thus, v, okay, x squared minus 2x plus 1, times du, which is 2. Come in this way so I can use my space. But we're like right into the derivative. Right? Above, we had to like rewrite the function, multiply it all together, combine like terms, stuff like that. But there's the derivative in red. What do you think? So far, so good? Okay, cool. Do you believe me that that's right without me proving it to you? Okay, that's good. Do you think we should leave it like that? No, what should we do? Huh? Multiply out. Yeah, let's do that again. All right, let's write it as simply as we can. And simplest form usually doesn't have parentheses in it. So let's distribute here and here. All right. Ooh. 2x times 2x 4x squared. If you'll let me, I'm going to do these two at the same time. Negative 4x and negative 6x is negative 10x plus 6. Whenever I distribute, I try to like combine like terms as I go. If each factor is written in standard form, they're going to come out in general, depending on if there's pieces missing. They'll come out relatively close to standard form. I got the second one too, so everything just gets 2 times bigger, so 2x squared minus 4x plus 2. And again, combine some like terms together. Okay, so 6x squared minus 14x plus 2. Right, so we'll use the UDV plus VDU setup. And just that little side work really makes that part easy. You just put the right pieces in the right place. Right, just put the puzzle together and then make it look a little nicer. Distribute, combine some like terms, and oh my goodness, what a shocker. It's the same. The same function. Of course it's going to have the same derivative. Okay? Has to. And that's actually a really common question, I think, with like kind of within these guided notes initially, is they'll say, hey, do it the first way, or do it like we learned it in chapter 2. Now prove to me with one of these rules that you get some. Which way did you like better though? The first way or the product rule way? Way easier, right? Now some of us might like the product rule because it's cool. I like it. But that was a lot more work, I think, right? Because I had to do my UV, DU, DV. I had to set up the product rule. I had to remember the product rule. I had to plug stuff in right. I had to distribute correctly and combine them. First way was just, all right, multiply it out, combine some like terms, power rule, and I'm done, okay? And so the question that kind of comes up, and I totally agree with this. So if you look at the words kind of right underneath this, right? People wonder initially, all right, why am I learning the product rule if I've got a better way? And I absolutely agree that if you can rewrite it as a polynomial, do it. In general, it's going to be fast. Because you can see that no matter what, we've got distributing to do, we've got combining like terms probably to do. So, and then the product rule on top of that, that just seems like, okay? So, second line there, about halfway through, if it is possible to rewrite it as a polynomial, they say always, I say almost always, but certainly as often as you're comfortable with, rewrite it, okay? X squared times sine of it. Can you rewrite that as a polynomial? Right? The issue with this is you've got an algebraic function right there, that quadratic, okay? You don't have to write the arrow, I'll come over here. Functions that are not algebraic are called transcendental. They transcend, they go above, the basic rules of algebra. That's things like trig, anything trig, exponentials and logs, stuff like that. Okay, and that list can keep going. Those are probably the only ones we're really familiar with at this point. But there is more. Okay, having that mixture of an algebraic function and then a transcendental one means we'll never be able to write that as a polynomial. Or if they were both trig functions, right? Something like that. Or maybe we just don't want to. Because you don't have to rewrite it. That's only a choice that we make, and it's usually the right one. If we can, sure, we'll do it. But either we don't want to, or in the case of this g of x right here, we just can't. Now we have to use the power. Right? And so that's what we'll do. All right. So here's our original function. I'm going to come off on the side over here, and let's see if we can make a decision about what we want u to be defined as, and what we want v. Maybe you do that in your head, but it's so much easier. And you're going to see when we get to the next rule, probably Monday, there's more going on. keeping track of u and v, du and dv is going to come in. Okay, so what do you think? What should u be? Yeah, x squared looks good, right? They're like, find where multiplication is. So that's really what you're trying to do, is where are things broken apart by multiplication? This is the product rule, so I'm looking for product. And then so v must be. Now, initially, we're only going to be doing 2 factors at a time. But this can be applied to 3 things being multiplied together, 4 things, 5 things, an infinite number. And I'll show you what happens. All right, so we got u and v. What else do you think would be worth writing down, kind of right underneath? Good. Du. So what's the derivative of u? Of course, with respect to x, so that's the variable we got. 2x. And then dv. The derivative of sine. And there's my side work. Put the parentheses around the x's or not. There it is. Good to go. Now I could say dy dx. That would be fine. I'm going to stick with g prime though, just so it's super obvious what I have. Because when I say dy dx, I don't know which function I'm looking back at. Of course, there's only one function in the problem, so it's not a really big deal. But labeling is your choice. And those are interchangeable at that point. Just for good measure, I'm going to write it down again. U dv plus v du. U dv plus v du. And then away we go. All right, u, x squared. Parentheses or not there, it's just a monomial, so parentheses aren't necessary. Times dv, okay, it goes on x. And having it all written down, man, it's just all right there. It's so easy. Ready to go. Plus v, okay, sine of x. Times du, we got 2x. Is there any distributing to do? Are there like terms to put together? No. The only question that remains is, what's the best order to write each of those terms? Because we've got these, we've got products in each one. If we're going to write g prime of x like consistently in some order, should we put algebraic stuff first and the trig stuff second? Or should we put the trig stuff first, the algebraic stuff second? Like, what's the best order? Should we do it like the first one, or should we do it like the second one? Which one looks better, feels better for you? I don't like putting the algebraic stuff first. And any trig stuff I'll just kind of dump at the end. So like I like the order here, x squared cosine x, the dot in between or not, and then plus 2x sine x. That just looks better. The thing that I think I really like about that, obviously coefficients got to come first. And then you've got powers of x's, right? Let me ask you this. What's the degree of just this term right here? You've got an x squared times a cosine of x. What do you think the degree, the total degree of that term is right there? 3. X squared times cosine of x to the first. When we have multiplication, we add exponents together. The degree of this is 3. The degree of this is 2. X to the first, sine of x to the first. So even that's in standard form. Love it. Done. We're not going to actually answer the question today. Find the slope of the normal line when x is pi. We'll kind of come back to the normal line stuff here in a little bit. I wanted to use this little space down here at the bottom to give you a chance to think about what we would do if we had 3 factors instead of just 2 being multiplied together. So hopefully you can see this. So, all right, problem done for now. What if our y wasn't u times v? Not just 2 things being multiplied together, but what if it was u times v times, what letter should we use next? A, B, C, D, E, F, G, W, right? That comes next. Okay, cool. So let's call this U times V times W. And just by showing you this one version, I'm going to go dy dx here because I called it y. Then you'll know how to apply it to 4 and 5. Usually that's as far as we'll ever go, if that. But let's think about what has happened so far. So, all right, so we had two things, right? We had a u times a v. They gave us a function that was just the product of two factors. Okay, so two factors to start. Look what we end with. Two terms, right? Two terms, two factors each. So we started with two factors. We end with two terms that have two factors in each one. Okay. How many terms do you think we're going to have? How many factors in each? You're not wrong. Let's just set it up. What you'll see is that in each of those three terms, there's only one derivative. Okay? We'll have a du in one of them, a dv in one of them, and a dw in the other one. Okay? The other ones will just be the originals. Now, the order, again, doesn't matter. But sticking with the order here, we did the derivative of the second one, and then the first one kind of went this way. That's what I'm going to do. U times V times dW. Plus, okay, so we did the derivative of the third one, kept the first two. Let's go down one. Let's do U times dV times W. Okay, cool. So we can take the derivative of the middle one. In order doesn't matter. So UV dW, UdVW. What's the only derivative we don't have yet? Du. Okay, so then what has to come right after it? VW. Good. Times V times. There it is. So if we had four factors, four terms, four factors in each. One derivative at a time. WX would be next, and we certainly would use that. We'd pick something else. Okay. So we're not going to use Y or X to substitute something that has Y or X. Sweet. How you feeling? Pretty good? Okay. I want to give you a chance to try it today. Go ahead and turn the page. We've got some practice back here, and I know that with these first two, we certainly could multiply them out first. But they want us to use a product rule just as good practice. So I think that that's going to be a good idea. And between today and the start of tomorrow, we'll do all six. You probably don't have time. I only have 10 minutes left. You probably don't have time to get all six done. So I don't know, like pick two or three of them. I'd say at least the first two to start, and maybe jump into that middle left one once you get there. And see how it goes. I'm going to talk a little bit as I work through them so you can see answers. But I'll give you a second or two to kind of get out in front of me so we can see how it's going. And I'll give me a chance to take attendance. Good. I'm going to do my U's and V's. Give it a shot, see how it goes. your first one before you do anything else. BD versus BD. The same spot. Yeah, right. Yeah. Now, as you start to make your way maybe across the g of x, pause for a second and just kind of join me just so that we're on the same page, whether you're doing this one or not. Go to g of x there, top right. What do we think u should be? What do you think? What's the best choice there? Yeah, square root of x, but writing it like right away, so it's differentiable, I think is going to save us a lot of trouble. As soon as you define something, get it to a setup, a style that's going to make it easy to differentiate. There it is again, differentiation, right? Easy to differentiate and also easy to combine, right? So, because eventually I'm going to have to multiply stuff together. When I multiply, I add exponents, and even when I take the derivative of u and I say, okay, like 1/2 x to the negative 1/2 is kind of like my initial power rule move there, I am going to leave it like that all the way through until the very end. Have your u's and v's, du's and dv's, have them in polynomial form throughout the entire problem. I am not going to rewrite that even as like 1/2x to the 1/2. Like I won't take care of the negative. And I certainly am not going back to radical form. Not until the end. Okay? Give yourself the easiest path, the path of least resistance with the derivative by writing it as nicely, right, as usefully as you possibly can. You prime, I guess. So u, let's to the 1, not changing. And v plus v du 1/2 x to the negative. Because I know I have to distribute. I know I'm going to have to combine like terms. And leaving it with rational exponents, even negative ones, is going to make that really easy because when we multiply x's together, we add their exponents. So your comfort level adding and subtracting fractions is going to come in. If you are not comfortable, don't guess. Have a calculator help you out. Right? If you can't get to there for that first, right, x to the 1/2 times 2x, you don't know that that's 2x to the 3/2. That's okay initially. do something to help you, but you want to start getting more and more comfortable with that as a 3x to the 1/2, 1/2 x to the 3 halves, 3/2 x to the 1/2 plus 1 x to the negative. Yeah, you got to do my books. Negative. And then combine like terms are same variables, same exponents. All my x to the 3 halves are all going to go together. All my x to the 1/2 are going to go together. All my x to the negative 1/2. And then I'll make the switch. Again, I got to add fractions. 2 plus 1/2. 4 halves plus 1/2 is 5. All my x to the 1/2, so negative 3 minus 3 over 2. So negative 6 over 2 minus 3 over 2 is negative 9. One of these there. All right, the completed version. So this is still g of x. And we'll stop right there. At least I will. Plus 5 halves square roots of x cubed minus 9 halves square x. 1 over square x I. If you wanted to put them together, make one single rational function. Your common denominator is actually 2 root x. The 2 from the fractions, the root x from that last one. So multiply through by what you need to, it actually comes out pretty nice. Just multiply through the first 2 fractions, or the first 2 setups, right, by just the square root of x. 3 halves plus 1/2 is 4 halves. Oh, nice. 5x squared. 1/2 plus 1/2 is just 1. Oh, nice. Negative 9. But what's boxed in is good with me. But just good practice to try to do that. All right, we have all day tomorrow to practice. Okay, only product rule stuff tomorrow. We'll finish this page, and then we'll see if we have anything else kind of floating around these next couple pages. Remember, like I said, short day tomorrow, right, with the late start Friday. So we get started like now, like 11:15, or normally end, I think, is when we start on Friday. So enjoy a little extra sleep if that's your thing. Nothing you need to do for me in anticipation of tomorrow. What's going on? Folks at home, you guys are good to go. I will see you mañana.
Thanks. Have a good day.
Thanks, you too.